Good morning, Bibhu Dutta Sahoo, sir.
Yes, good morning. Yes.
Uh, Once again, I welcome all the participants to this FDP organized by Gauhati University Institute of Science and Technology. Today, we have with us Dr. Bibhu Dutta Sahoo. He is an associate professor at the Department of Electronics and Electrical Communication Engineering in IIT Kharagpur. Also, he is professor in charge of the Advanced VLSI Lab there. His research areas include signal conditioning and mixed signal VLSI design, as well as RF and microwave circuits. He has been awarded with a lot of awards and accolades. He has a lot of publications in reputed journals and conferences. So I would like to hand over this session to Bibhu Dutta Sahoo sir so that he can deliver his talk.
Yes. Good morning, everyone, and thank you for the introduction. Uh, um, I believe this talk is being recorded, so you can also listen in later on, and we can have also offline discussions if there are certain things that are not very clear. The title of the topic that has been given to me is today's topic is low power analog IC design. Let me share the screen. So I hope you can see my screen, right? Is my screen visible?
Yes, it's visible.
Okay. Okay. So I will switch to a pointer mode. So I think you can see my pointer as well. Okay. So basically, I've broken this topic down, this thing into 4 sections. Okay. In the first part, I'll talk about limits of power consumption in an analog circuit, and this has mostly been derived from Eric Vitoz's paper on frequency dynamic range power in trade-offs in analog circuit design. So there is a typo here. In trade-offs in analog circuit design book. So I have used that as the thing. Then we'll talk about, in the context of one of the major blocks, which is the data converter, either an ADC or a DAC, how does scaling and other things impact the performance? So the reason is, I'll talk about that, is low power is achieved because of the scaling, where we scale the devices, resulting in the voltage supply being scaled and therefore the power being reduced. So that I'll talk about that. Then I'll take a sample example how a basic simple ADC, how the power and area and all those things are compared. And in the end, I'll talk about an all digital circuit used to realize an analog circuit, analog low pass filter or analog something interesting, and that is robust to supply voltage as well as other scaling trends. So that is how I'll conclude the talk. Okay. If there are certain doubts, we can address them as we go along. Also, we can if there are things that you can take a note, and we can look it up later on towards, offline. You can send me an email and I can answer those queries as well. So in order to derive the limits of power consumption, so we'll take a simple example where we have a GMC integrator. So this is a GM device which is integrating onto the capacitor. And you know that integrator is one of the fundamental building blocks in lot of circuits, like a low pass filter can be realized using this, delta sigma ADC can be realized using this. And mostly ADCs and low pass filters are some of the key building blocks in an analog system. Okay. Now, the supply voltage is defined as VDD over here, and input voltage is given to this. And the output voltage is at the output of the integrator. Now, what is shown here is the output swing, which is given as V peak to peak. And we assume that the output current that is charging and discharging the capacitor to give you this swing is equal to the current being drawn from the VDD. So this assumes that there is 100% efficient transconductor, which is not really true. So that means it's a class AB kind of an operation where you only operate with the output current. You flow the output current whenever you are charging or discharging, but there will be some amount of quiescent current flowing in this transconductor, and therefore there will be certainly not 100% efficiency in giving you the required swing. Now, if I look at this waveform of the output voltage, therefore the output average current is given by the frequency times the capacitance times the peak to peak swing. So this is the output average current. The average power consumption is therefore given by average current times the supply voltage, which is VDD times this thing. Okay. Now, what we do is we multiply VPP on the numerator and denominator. We get this expression over here. The noise current power spectral density is 4 kT gamma GM. So this is a well-known thing. This is the noise current, power PST, and the gamma is typically 1 in lower technology nodes. Okay, 2/3 in higher technology nodes like 0.18, 0.25 and higher. It is 2/3, and sometimes it is a little more than 1 as well in 28 nanometer. That's what we are seeing. The signal to noise ratio SNR is given by the RMS value of the voltage, the power of the signal, which is VPP square by 8, because this is a peak to peak swing. So it is going to be this divided by 2. This is VPP by 8. Okay. This is the signal power. The noise power, when we have this power spectral density and we are integrating onto the capacitor, this power spectral density of the current thing onto the capacitor, the overall integrated noise power on the capacitor is KT over C. This is a well-known derivation. And therefore, this implies that the peak to peak swing square is given by 8 KT SNR by C. Okay. So we are just solving this expression over here. The power consumption can be written as, therefore, P can be written as the VPP square here is replaced by this expression over here. Okay. So therefore, the power consumption of the circuit, you can see, is a function of temperature. As you increase the temperature, of course, it will keep on increasing. As you increase the frequency, the power consumption will also increase. But keep in mind, this frequency in an analog circuit translates to the bandwidth of the circuit. Typically, the 3 dB bandwidth, either it's a low pass filter or any sampling circuit, any op amp in feedback with certain bandwidth, is proportional to the SNR. The higher the SNR I want, the more power we have to burn. So this is a very clear indication that if we want more and more signal to noise ratio, we have to burn more and more power. It is of course proportional to the supply voltage and is inversely proportional to the peak to peak swing. So if I keep increasing the swing, then certainly my signal power will keep on increasing, and therefore my power consumption is going to reduce for the given amount of SNR. Now, what does it say here? That means if I want to minimize this for a given SNR, I should have the peak to peak swing as close to the supply voltage as possible. If this is 1, then I get VDD over VPP is 1. That is the minimum power that we can achieve for a given SNR and for a given bandwidth. So power consumption minimized by maximizing peak-to-peak signal swing, that is with rail-to-rail operation, VPP equal to VDD, and P min is given by this expression, because VDD over VPP equal to 1, so 8 kT F by SNR. So power is proportional to frequency, which is now, as I said, the frequency is nothing but an indication of the bandwidth of the circuit over here. In case of a low pass filter, it is the bandwidth. In case of other circuits also, it will turn out to be the bandwidth. If I want to operate at a higher frequency, that means I have to enhance the bandwidth of the amplifier. Okay, so now we'll define something called a figure of merit. K is power divided by KT, and F is replaced with bandwidth and SNR. Okay, now this, so here we will say that power divided by KTB SNR is 8 times VDD over VPP. Now the figure of merit is K, as the smaller it is, the better is the overall analog circuit in terms of power consumption. Okay, so this K turns out to be 8 VDD over VPP, smaller the better, which has a minimum value of 8. This will have a minimum value of, theoretical minimum value of 8. Okay, so now on this plot we see that x-axis is the SNR, and minimum power per joule is per pole. So pole means the bandwidth defines the pole of the filter. Minimum power per pole, which translates to the energy. So you can see that this is turning out to be a straight line for a given SNR. Okay, so if we have to operate from an SNR of 30 dB to 90 dB, you can see that our power increases by a few orders of magnitude, 6 orders of magnitude. Okay, so certainly as we keep increasing the SNR, we would have to burn more and more power. If we have to increase the bandwidth, means our pole frequency is going to increase. Okay, and therefore pole frequency increasing, resulting in more and more power as well. Okay, so that is the bottom line. So this kind of sets the trend. Now the K-min, the figure of merit, constitutes an absolute minimum, not accounting for many non-idealities. Okay, in practical analog circuits, there are many non-idealities that can seriously degrade the K factor far beyond K minimum. And when we say degrade, means it is going to, as we said, K, the lesser it is, the better is the circuit. Okay, so that means it is going to increase the K. Okay, so now current inefficiency. So as I said, we have assumed the current that is charging this capacitor is actually the current drawn from the supply. So now certainly this is not the case. You have to burn certain DC current to bias this. So there will be not 100%. So that is called current inefficiency. Now then there is a linearity requirement. So this circuit has to be a linear. So in order to make sure that it is linear, we might have to linearize the transconductance over here, and there we have to burn more and more current. We need additional bias circuits. We also have to make sure that we are meeting the matching requirements. So we have to make the devices bigger. When we make the devices bigger, we increase the capacitance. And as we increase the capacitance, our power consumption increases. Okay, so therefore this will also going to increase the overall power and make sure that the K becomes bigger and bigger. The figure of merit gets worse and worse. There are additional noise contributions like flicker noise and from other devices. So flicker noise, we have to make sure that we are not flicker noise dominated if we are doing any low frequency design. So we have to make sure that we mitigate the flicker noise, and that can be mitigated by either correlated double sampling, the standard techniques that are used, or by using something called chopping. And as you know, chopping would result in some switching on the input and some switching on the output. And if I have an analog circuit which has switching on the input and the output, the output of the op amp will take some time to settle. That means you have to burn more current to make sure it settles. Similarly, on the input side, if there is switching, that means there will be some amount of settling issue for which you have to increase the bandwidth, and therefore you have to burn more and more power. So that's why the flicker noise contribution actually degrades the figure of merit or increases the K factor. There are parasitic capacitances. And of course, there is something called charge injection, which is a very which has a very detrimental effect on the overall linearity of the circuit. And in order to mitigate charge injection, you have to do something called bottom plate sampling, or you have to do some kind of charge injection cancellation using some dummy circuits. Okay. In this in this 2-hour lecture, I cannot go into all the details of how flicker noise contribution is mitigated, how charge injection is mitigated, and how the linearity requirement impacts the power. But the bottom line is, whenever we try to do something, design something with low power, we have to we know that if I need a higher SNR system, I have to burn more and more power. Okay. Now, as I said, the next topic that I will get into is the scaling trend and impact on data converter design. I have taken this as one of the key analog blocks. So this one was dealing with low pass filter, okay, and then we'll go into data converter design and get to the see how the scaling trend, which is supposed to reduce power, but sometimes it actually leads to burning more power in an analog circuit. We have to resort to other means to reduce the overall power consumption of the analog circuit. So any question on this part of the lecture? Any questions on this?
Sir,
Yes.
the K factor has the minimum value of 8.
K factor has the minimum value of 8, provided we can swing all the way to rail to rail.
The 8 comes from the signal shape is sinusoidal.
Yes.
If it is not sinusoidal, then what will happen to this?
Okay. So the thing is that typically the conventional method of analyzing any analog circuit till as of now is that you apply, whenever we say an SNR, we apply a single tone, compute the signal to noise ratio, right?
Okay.
Now, when you talk about if the input is not sinusoidal, then that means, suppose, for example, a typical example is an OFDM signal or any biomedical signal. The signals are certainly not sinusoidal, right? But the problem is that when we when we have, I cannot get into that analysis. The SNR for a sinusoidal signal is something. SNR for a Gaussian distributed random signal is something else. Okay. In fact, the sinusoidal signal has a pessimistic SNR. Means if we can meet the sinusoidal SNR for a sinusoidal system, then certainly we'll meet the SNR for any other kind of signals. So that's why all the analysis in analog circuits is done by considering a sinusoidal single tone input.
Okay, sir.
Okay.
Sir?
Yes.
Sir, is it allowed to stretch the VPP up to VDD? Won't we have that non-linearity?
No, yeah. So that is what I'm saying. So this is that's why the theoretical minimum limit, right?
Okay.
8 is a theoretical minimum limit. As you approach the supply voltage, your linearity will degrade.
Yeah.
Okay.
Yes, okay.
But in the end of this course, I will show a circuit which actually can extend the VPP all the way to VDD.
Oh, okay.
Okay. So that is a digital technique for realizing something. Although the VPP still it cannot approach VDD, but it will, because it is a digital circuit, it can swing. It can swing all the way from VDD to ground. But I would not say that the output signal swing is VPP. Okay. Is equal to VDD. So that's why I said that this is a theoretical limit. Theoretical limit. Smaller the better, which is a minimum value of 8. So this is a theoretical limit. You cannot beat this at this point.
Thank you, sir.
Okay. Now the scaling trend. So we will talk about certain things about scaling. So this has been taken from the presentation given by University of Toronto professor. What do you call this? These plots have been taken from his slides. So I've cited his slides, the source where I have taken it from. So now, first we'll talk about you keep in mind first, GM is a transistor is a GM device. So we'll talk about how GM scales with technology. Then we'll talk about how GM over GDS. Okay, and GM over GDS is nothing but the intrinsic gain. Okay, how does intrinsic gain scale with technology? So now let us look at this plot here. Okay, as you can see, the GM transconductance, if I consider 180 nanometer all the way down to 65 nanometer, you can see on the x-axis is the drain current. As I vary the drain current, the GM follows the same pattern no matter what is the technology node. Now, so that means we can say safely that GM does not scale with technology. Okay, which is a good thing. Okay, because that means that we are not compromising by scaling the GM. Now let us see what happens. GM is not scaling, but GDS is dropping, right? Sorry, GDS is increasing. So therefore RO is dropping. So the product is reducing. Okay, so therefore the intrinsic gain, if you compare for 180 down to 65 nanometer, so you can see that 180 nanometer, the intrinsic gain was pretty high. GM over GDS was close to 50 or close to 70. Yeah, sorry, it was close to 55. Okay, of course, as the drain current increases, as you know, the RO drops of a transistor, right? So this is a basic thing how the device works. If I keep increasing 1 over lambda ID, RO is equal to 1 over lambda ID. And therefore, as I keep increasing, so therefore the GM over GDS intrinsic gain is going to drop as I keep cranking up the drain current. Now, these numbers are all obtained for minimum gate length. Okay, why are these for minimum gate length? Because minimum gate length is what gives you the maximum operating FT, the transit frequency, and therefore gives you the maximum operating frequency. Now 130 nanometer drops down, then you can see 90 nanometer and 65 nanometer we are well below 10. Okay, so that means there is hardly any gain that we get when we have used transistors, and we have to come up with fancy techniques to improve the gain. So this is not a good thing. Okay, GM over GDS. So that's what is written. Transconductance is for all practical purposes independent of technology node. Okay, for velocity saturated channels, ID is given by this and GM is given by this expression here. So in a way, in all these, that the transistors are almost velocity saturated. Certainly in 65 and 90 it is, 130 and 180 also they're approaching. So with constant field scaling, if W gets scaled down by a factor, then Cox gets scaled down by a factor of K and GM stays constant. Okay, intrinsic gain reduces as technology scales down. The maximum intrinsic gain in 65 nanometer is less than 20% of the maximum intrinsic gain in 180 nanometer. So you can see it is less than 20% of 180. So we have compromised the gain significantly as we scale down the technology, and 28 nanometer and below are also even worse. I mean, actually 28 nanometer and 16 nanometer FinFET, they go for high K dielectrics and they try to maintain this intrinsic gain pretty close to this much. There will be 7 or 8 or something like that. Okay, so therefore this drops. Now what is the potential speed improvement? So this is the normalized FT. Okay, so as a function of drain current. Okay, again minimum channel length is chosen and speed potential normalized to 0.18 micron node. So keep in mind this is a normalized frequency. That means the 180 nanometer has a speed given by this green 1, means if it has a speed of 1, 130 nanometer is slightly better. It is slightly better, 10% better, 10-20% better. Okay, the 90 nanometer is 3 times better. We should be operating in this region, so it should be 3 times better. Okay, now as you now 65 nanometer is significantly better. Okay, so we get 5.5 times better. So you can see that as we scale the technology nodes, the FT given by this expression, GM doesn't scale, but these things scale, and therefore you get a speed improvement. We have already seen that as technology scales, GM doesn't scale. So GM is the same. So the numerator stays the same, but the denominator CGS, because for the same size of the transistor, L has reduced, same width, we get more and more. We get more and more current, and therefore CGS to carry the same current, we need a smaller device. W will be smaller, and therefore W smaller means the CGS, CGD, and CDB are going to be smaller, and therefore our FT is improving. By scaling down, potential speed improvement can be obtained. Almost five times speed improvement is obtained in 65 nanometer process over 180 nanometer. Now keep in mind, if we go to 2816, this becomes close to 10 and also 10 to 15 times better. So that means we can get pretty good speed with 28 nanometer and 16 nanometer. So we don't have access to 16, 12 nanometer FinFETs, but 28 nanometer, we have seen that it is significantly faster. So now, what is the transistor efficiency? The efficiency of a transistor is defined by GM over ID. Okay, means GM is the voltage to current converter. How efficiently does it convert from voltage to current? And ID is the amount of current that you get. So GM over ID is therefore the efficiency, and we can clearly see that the efficiency of the transistor, right, does not change with technology that much. So this has been shown so we should be operating in this region where the efficiency is maximum, and maximum efficiency is nearly independent of technology. Okay. Now we mentioned that nonlinearity is a big concern. So now there are two kinds of nonlinearity when you are trying to design a circuit which gives you a certain gain. The gain is product of GM times GM divided by the GDS, right? So now there will be therefore two components to nonlinearity. One is the GM nonlinearity, okay, and the other is the GDS nonlinearity, okay. So you can see that the 90 nanometers, the lower technology nodes are more nonlinear, okay, compared to the lower nodes, okay. So 180 nanometer is much better than 130 nanometer, and then 90 nanometer is the best, okay, is the worst in terms of nonlinearity in the GDS nonlinearity. So this increases with scaling, which is a very bad thing. But the GM nonlinearity, interestingly, does not scale with scaling, okay. But I think in 28 and 16 nanometer, it does scale with technology. So slightly, but not that bad, okay. So that means GDS nonlinearity is increases with scaling, which is a bad thing, and GM nonlinearity stays constant, does not change with scaling, so which is a good thing. So because GDS nonlinearity, the increased GDS nonlinearity makes design of linear op amps a challenge in scaled down CMOS, okay. So this becomes a challenge to achieve linearity in the scaled CMOS process, okay. The another thing that is also detrimental for design, and especially in some systems like DAC designs, okay, where one bias node is driving a ton of transistors, biasing a ton of transistors, that time is the gate leakage. What happens is that the gate leakage results in the voltage going to each and every transistor different. Ideally, you want the same bias voltage to go to all of them. But since it is connected to a lot of gates, each of the gates have a leakage current, and thereby our voltage drops as it goes to different transistors. So our DACs, there is a huge amount of variation in the current flowing through the individual current sources, and that is very, very detrimental. So as you can see, the gate current in amperes, okay, so these are in nanoamperes and picoamperes. So 180 nanometer has the lowest amount of gate leakage, and of course 90 nanometer has the worst amount of gate leakage, and 28 nanometer is way higher up, okay. And therefore for 28 nanometer, we are not using the smallest technology channel length, we are using thick oxide devices. And the gate leakage increases because the oxide thickness reduces. But in 28 and others, the oxide thickness reduces, but they have gone for high K dielectrics and all. They try to minimize the gate leakage, but still there is a significant amount of gate leakage. gate leakage current dominated by tunneling current. Designing highly linear becomes very challenging as the held value may also leak out. The gate leakage would cause the voltages on certain nodes leaking out, and also not only that, also the bias currents of various blocks also changing just because the gates start leaking. Okay. Now, next thing is the noise factor, as we talked about. See gamma, the gamma factor, noise factor gamma increases with reduced channel length. So we said that in lower technology nodes, the gamma is less than 180 nanometer and below, it is close to 2/3. As the technology scales down, we see that the gamma factor significantly increases. That means the noise contribution of the circuit also increases. Now, as the gamma increases, the SNR of the system decreases. Okay. Not only the data converter, but for any other block as well, the SNR significantly drops. Now let's look at the. This is an interesting plot. This is obtained from NCTU, National Chiao Tung University slides. Now what this is showing is when we have. This is showing the variability of the transistors. Now, why did we bring this up in the low power context? Now, as you can see, as the technology node scales, okay, down, the threshold voltage of the transistors varies significantly. For the same device, if I manufacture 10 of them, same W over L, the threshold voltage will significantly vary because the devices are so small, there is huge amount of variability. Now, but in the higher technology nodes, you see that they are pretty nicely controlled. They are around close to, certainly we'll throw out these devices. These devices are useless. So that means we have a poor yield. Yield means how many of the circuits perform reliably. So here you can see in low technology nodes, the yield drops significantly. Okay. Now, therefore, we say that the variability of the transistors increases with scaling, which is a bad thing. Now, if this is increasing with scaling, so how does it impact power? Why does this impact power then? Anybody has any hints? Why does this variability have to do with power then? So what happens is, now the variability is large. So now in order to control the variability, what do? We have to make the devices bigger. And when we make the devices bigger, what happens? The capacitance increases. And therefore the power increases. So, so therefore, this variability is a big factor. And in order to counter the variability, we go for bigger devices. And bigger devices also reduce the amount of flicker noise. As you know, the flicker noise is inversely proportional to the area of the transistor. Okay, W times L. Yes.
You were telling us that you are making a bigger device, but you are also scaling the device at the same time.
Right.
How to make a bigger device if you scale down these devices?
No. You what you do is basically we want to make sure that the variability is small, right?
Yes.
So now, if I want to reduce the variability, the area of the transistor has to be increased, right?
Yes.
Now, in order to increase the area, what can I do if I have to maintain the same current? I will reduce the L and increase the W. I'll increase the L and increase the keep the aspect ratio the same.
Yes.
Now, when I try to keep the aspect ratio the same, W and L, I keep increasing what happens to my FT? FT drops. Now, as soon as my FT drops, now I have to get back the FT. So what do? I burn more current. I increase GM. And how can I increase GM? By burning more current. So therefore, I have to burn more power. Does it make sense?
Yeah.
Yes.
Sir.
Yes.
when you are comparing two technologies, for example, say 28 nanometer and 65 nanometer, or maybe 180 nanometer, you are saying their GDS is increasing, okay? And as a
GDS
result,
of scaling, yes. As you're downscaling,
GDS,
GDS is increasing. Yes.
yes. So my point is, if I scale up, say 28 nanometer devices to 65 nanometer, and then compare the performance, uh, how do you see the comparison?
So you are saying, see, all these comparisons are done for minimum gate length. So
Yes,
what
sir.
you're saying is, if I go for 28 nanometer technology, but we make the gate length bigger, right?
Yes, sir. Yes, sir.
Then we lose the speed advantage. FT improvement doesn't come,
Okay. Okay.
right?
So
Because
will
we are
it be
going to lower
inferior to
technology now. Yes, go
will
ahead.
it be inferior to the standard 65 nanometer technology, or how do you compare it?
It will be comparable. It will be
Will be
comparable to
comparable.
65. Yes, the speed wise, it will be comparable to 65.
Okay, so thank you.
Okay, it will be comparable to 65 because the speed is purely a function of the time it takes for the thing to travel, right? So if you scale the L, then certainly your speed is going to drop. If you increase the L, your speed is going to drop, and now to get back the speed, you have to burn more current. You have to crank up the GM. So that's where the power comes into the picture. So increased spread makes the design of op-amps and other precision circuits very, very challenging as well. Not only does it compromise the power, but it also makes sure that your precision circuits work as reliably as possible. So you have to make sure that they do not change too much as the technology scales. Okay.
Sir,
Yes.
digital circuits are scales below to 7 nanometer nowadays, I think.
5 nanometer, I have seen. Samsung has 5. Samsung ST have 5 nanometer technology as well.
Is the analog circuits are also scaled down to such
Yes,
low
yes, yes,
level?
yes, yes. Currently, I am having a collaboration with a company where I'm working on 7 nanometer FinFET, and the analog circuits are designed in 7 nanometer FinFETs as well. So we are building a 112 gig SerDes. Okay, so that is being designed at 7 nanometer TSMC, and we have done the TIA and all operating at a pretty good speed. Like probably each TIA, there are 4 channel, 112 divided by 4 is close to 30 gig. Each TIA is operating. TIA is trans impedance amplifier. But there we are not using all transistors which are 28 nanometer, 7 nanometer channel length. We are mixing transistors. There are 3-4 flavors of transistors: thick oxide, thin oxide, midway between that and all. So we are using all the variations of that and making only the speed critical devices minimum channel length. Others we make it larger.
Okay, sir.
Okay. So I hope all these things, all these points, I just want to reiterate that these things translate to power consumption. Okay. So I hope that is clear. So that's why I started off with the power consumption expression first in an analog circuit. But keep in mind the F in analog circuit will be replaced with the bandwidth. Okay, it is not the switching frequency, because in analog circuit there is hardly any switching. It is mostly analog signal, so there is no switching happening. Analog swing is what is happening. In a digital circuit there is switching happening. Okay, now there is supply voltage scaling. Now here is the thing. This is from Custom Integrated Circuits Conference 2005 paper. Okay, let us see, why does analog design becomes challenging as the supply voltage scales. Okay, so if you see 0.25 nanometer, typical rule of thumb that has been followed until 90 nanometer is the supply voltage is 10 times the technology node. So 0.25 micron supply voltage is 2.5 volts or 3.3. Okay, so like that, 0.35 micron supply voltage is 3.3. So that is a typical rule of thumb until 90 nanometer. And after that, the supply voltage has been kept almost constant at 0.7, 0.8 volts. In let's say 7 nanometer also it is close to 0.7 volts, 0.77, 0.75 volts is the supply voltage. So yeah, x-axis is the technology node, y-axis is the supply and threshold voltages. So what is being shown here is that as the technology node scales, the analog supply voltage is scaled down along with it. But you can see that the analog supply voltage has reduced by a factor of 3 here, roughly. But the threshold voltage is not scaling by a factor of 3. The threshold voltage scaling. So now you can see that the swing here that we can get is much bigger than the swing that we can get here. Now our SNR is a function of the swing, right? VDD over VPP. So now certainly you will get better SNR in lower technology nodes and poor SNR in higher technology nodes. But certainly your bandwidth will be lower in this technology node and bandwidth will be higher. So there is a trade-off over there. And digital supply voltages scale pretty aggressively. So that has been there. So you can see that 2.5 down to 0.5 also they have gone down in nodes. So digital supply scales and that is not a problem at all. Digital VD scaling more than analog VDD scaling. Okay. Supply voltage scaling more aggressive compared to threshold voltage scaling, and this is done to minimize leakage. Otherwise, if you go for higher and higher supply voltage for lower technology nodes, you will increase the amount of gate leakage because tunneling will increase, and also it might break down the device, and it will also, if tunneling current is large, also it will damage the threshold voltage with time. Okay, because you will trap more and more charges in the gate, and that would change adjust the threshold voltage of the device. So certainly you have to scale down the analog supply voltage, but this analog supply is scaled less aggressively compared to the digital supply voltage. Okay, now let us see, as I said that ADC is one of the data converter. ADC is one of the most challenging blocks in an analog system. So we'll show here on the x-axis, this is taken from this website called converterpassion.wordpress.com. So what it shows here is the supply voltage on the y-axis versus the channel length for different with different technology for ADC designs. Okay, so as the technology scales down, okay, these are the different supply voltages chosen in different nodes. Okay, so the lowest supply voltage is the state of the art that has been chosen. Okay, so the lowest supply voltage is I think 0.2 volts that have been used for some ADCs. Majority of ADC designs have VDD greater than 1 volt. Majority of the ADC designs, these dots correspond to the thing, and this is the nominal VDD trajectory that has been followed, and you can see that as the technology scales, we from 500 nanometer to 130 nanometer, the trajectory followed pretty well, right? But from 130 down to 32 nanometer, this is not scaling. The supply voltage is not scaling down as much. Okay. However, some ADCs have used VDDs which are commensurate with digital VDD, and these are especially for VCO based architecture, which is the voltage controlled oscillator based architecture. And these VCOs are realized using digital circuits, digital inverters, and therefore for them the supply voltage can be scaled significantly. And that's why VCO based ADCs are becoming more and more popular these days for quite a lot of applications. Okay. Now this is another thing. As the supply voltage scales, again it's taken from the same website. It shows the noise floor of the data converter, how the noise floor of the data converter varies with the technology node. Now, what is interesting is that that's why they say that 180 nanometer is a very sweet spot for analog design, because in 180 in this range you can see that the noise floor is minimum. Okay, this is a minimum noise floor achievable. Now, in higher technology node, you have poor performance. The noise floor dB per hertz is poor, I mean, but in 180 nanometer it is even better. But as the technology scales down further, your noise floor goes up. Now, why is this worse? Probably because the transistors in those days, they were not, I am not sure why this trend follows here, but 180 and 250 nanometer are pretty mature processes and they have a pretty low noise floor. Okay. Now, there are two kinds of data converters. One is a Nyquist rate converter and the other is the delta sigma converter. Nyquist rate converters, the red line is the noise floor of a Nyquist rate converter, and the blue line corresponds to the delta sigma converter. So as you can see, as the technology scales down, your noise floor gets compromised, therefore your SNR degrades. So scaling of supply voltage, reduction in signal swing, reduction in SNR. Okay, achieving an SNR of X dB in 10 kilohertz band, this is very important, is not as attractive as achieving the same in 1 gigahertz bands. Although this plot shows that noise floor scales down, but all these ADCs which are defined by these dots, they are for different bandwidth. So somebody will say that I'm achieving a very low noise floor for a 10 kilohertz design, and somebody who achieves the same noise floor at 1 gigahertz design, that this is much more challenging. So this might not be a fair comparison, but it tells you roughly that scaling down becomes very challenging. Scaling leads to very challenging noise floor constraints, and therefore in lower technology nodes, you might have to burn more and more current to reduce the noise floor, because the only way you can reduce the noise is by burning more and more current. Noise is the random variation of the electrons of the charge carriers. Now current is the rate of flow of charge carriers. So if you just increase the current, the amount of random variation will reduce because the number of carriers are large. So that that way you can think of it. And therefore your noise floor will, in order to reduce the noise floor, you have to burn more and more current, or your power consumption increases. So relative noise floor is given as SNR plus 10 log of bandwidth. This is a simple expression, okay, which has been used to get this plot. Now, we have seen that scaling is not good. So what does this suggest? That scaling is not too good for analog circuits, because noise floor increases, power consumption increases, and you can see that supply voltage cannot be scaled drastically. So what can we do? So what we can do is, let us see if we can build a sloppy analog circuit, okay, with low power, and can we do something using digital circuits? Because if you see energy femtojoule per gate, the logic gate power drops with technology scaling. Okay, it drops significantly by 1, 2, and 3 orders of magnitude. This energy drops, and the number of gates that can be packed increases also significantly. So therefore, not only does the energy per gate reduce, but the number of gates that can be packed in lower technology nodes is more and more. Therefore, can we build sloppy analog circuits in low technology nodes to reduce the power and use digital circuit techniques, to compensate for the analog performance issues? Okay. So this plot has been taken from Boris Morman's slides, and this plot has been taken from TSMC. The gate density thing has been taken from the TSMC website. TSMC is some presentation, so I've cited the source here. So now, if you see, state-of-the-art 10-bit ADCs consume 1 milliwatt and megasamples per second. Energy per conversion is 1 nanojoules. Energy equivalent number of gates is 166,000 gates. This nanojoule corresponds to 166,000 digital gates. So if I can reduce the analog power by making a sloppy analog circuit, and if these many number of gates can be used to compensate, figure out what was the sloppiness in the analog circuit, I can certainly win by using digital circuits. So that's why, to achieve lower power in analog circuits, we go for a digitally assisted analog circuit. Now, in this 2-hour lecture, it is difficult to get into how digital assistance is done. But digitally assisted, if you want to reduce power in analog circuits in nanometer CMOS, the best way is to use as much digital gates to compensate for analog non-idealities. Okay, so this is another interesting plot which shows that as the feature size reduces, okay, feature size on the x-axis, these are for various SNRs. This is SNR of 100 dB. Okay, now if I want to achieve so what does this plot say is that if I want to achieve, let's say, 30 dB of SNR, okay, 30 dB of SNR, in order to achieve the 30 dB of SNR in lower technology node, if I want to have a sloppy analog circuit, then I would need roughly, I would say, 10,000 analog gates, 10,000 digital gates to compensate for the non-idealities, right? But as the technology, as I need higher and higher SNR, let's say we go for 60 dB. 60 dB of SNR, to achieve 60 dB is equivalent to as if we have 2.5 lakhs of digital gates. Okay, and to achieve 70 dB, it will be a humongous amount of in lower technology node, it is impossible to achieve close to 70 dB of SNR because we are thermal noise limited. So that's why this point has been given. So you can see that it is impossible to achieve higher and higher SNR in lower technology nodes. So that's why these are asymptotically increasing. But the energy consumption of an ADC for different SNRs is equivalent to these many gates on the y-axis. So now let us say I want to achieve something, an SNR of 60 dB. I'm over here. Then I can reduce the power of I can use a sloppy analog circuit and use close to 100,000 logic gates to compensate for the sloppiness. I would achieve a lower power, overall lower power design. So what is this? Therefore, the conclusion is for SNRs less than 50 dB. So 50 dB is somewhere here. Additional digital processing is expensive. For SNRs greater than 50 dB, using a few tens of thousands of gates has hardly any impact on the overall energy consumption. Okay, so therefore you can see that 60 dB ADC, the ADC which is achieving 60 dB is equivalent to as if I have got 250,000 gates, logic gates. Now, if I can reduce the power of the ADC and I've used the 20,000 logic gates to compensate for the analog non-idealities, I can reduce the overall power consumption and bring it down significantly. Okay, so here we have two things that should come out. Scaling helps to a certain extent in reducing the power, but not that much for analog power as much. Now, to reduce the analog power consumption, what we can do is we can go for sloppy analog circuits, okay, and compensate for the sloppiness of the analog circuit. Suppose I have a low op-amp gain, can I compensate it in digital domain? Okay. If I have more nonlinearity, can I do some nonlinearity correction in digital domain? So therefore, go for digital circuits as much as possible, but you have to carefully simulate and analyze the non-idealities and how the digital circuits are going to compensate for the analog non-idealities. Any questions on this part of the talk? Any questions on this? Okay. So I'll move on to the next one. So I'm picking a pipeline ADC as a test bed to show how the power, area, and speed and resolution optimization come into the play. So let's take a 2-minute break and we'll resume in 2 minutes on the pipeline ADC, and then after that I'll go into the all digital. Any questions? I can take a few questions now. Okay, so then give me 2 minutes. We'll resume in let's resume at 10:35.
Okay, sir. Okay.
Okay. I will resume now. Is that okay?
Yes, sir.
Okay. So pipeline ADC is actually, I've taken this as a test bench as an example because this involves both analog as well as digital circuits. Okay, and digital circuits can be heavily used. Now, if you say why not SAR ADC, because SAR ADC does not have op-amps, you need not have an op-amp in a SAR ADC, simple comparator will do. So SAR ADC is certainly much more amenable to scaling and is much more robust for low power, but it cannot achieve high speed. But pipeline ADC can achieve pretty high speed. So the pipeline ADC works like there are multiple stages. Each stage is realized with a sub ADC, which resolves a fewer number of bits. Then those bits are converted to analog voltage and subtracted from the input, and then amplified to generate a residue. And the amplification is done by using an op-amp, and the amplifier gives a gain of 2 to the power of n1. So however many bits we resolve, and the +1 corresponds to the redundancy in the system, which is needed to overcome certain non-idealities in each of the stages. Now, the residue voltage is then digitized by the next stage, and when the next stage is digitizing the residue voltage, the first stage is taking the next sample, and that's why it is operating in a pipeline fashion. Now this block over here is combination of subDAC and the summing node, and the amplifier is called a multiplying digital to analog converter. Now this residue is digitized by the remainder of the ADCs to P minus N1 bits. Now remainder of the ADCs can also be back-end ADC, can be realized with multiple stages, but in order to analyze the power area trade-off, we will just take the simple case where there is one stage and then there is a back-end ADC resolving P minus N1. So let's say P is 10 bits and we are resolving, let's say, N1 equal to 2 bits. So then this stage is resolving roughly 8 bits. Now these bits are combined using a digital circuit, which should combine with the gain inverse of this gain and gives us the resultant P bit digital output. Now, as you can see that this analog gain and this digital gains have to match to get the real performance. Okay. Now, as technology scales, getting the analog gain, this kind of gain, gets more and more challenging. Now, if getting this gain is getting more and more challenging, can we do something here? What if we can, instead of this much gain, it gives you some other gain? Can we estimate that gain and then use that inverse value over here to combine? And that is what is called, you are going to use these additional digital circuits to give you the to compensate for this analog performance degradation. Now let us say this stage of the ADC. Suppose now somebody might say that if I am resolving 10 bits, if I have an overall 10-bit system, I can resolve 1 bit in the first stage, 9 bits in the second stage, in the back-end stages, 2 bits in the first stage, N1 equal to 2, and let's say 8 bits in the this stage, or 3 bits over here and 7 over here, or 4 over here, 6 over here, any possible combination. So now how do you say which is the best choice of combination of the number of bits? Okay, and what will be your criteria? That gives you minimum power. That means I want to minimize the power consumption of the overall ADC, 10-bit ADC. So that is the optimization problem. So P equal to 10 bits. What should be the partitioning? Let's say this is a 2-stage ADC. First stage resolves N1 bits. Second stage resolves P minus N1 bits. What the optimization problem states that what should be N1? Okay, so that the overall power consumption of the system is as small as possible. Okay, that is the goal. So I hope the optimization problem is clear. And there are some papers which have done this optimization, but this is an interesting problem if anybody wants to work on as a research topic. they can also choose this and come up with different optimization algorithm. You can use machine learning and others to achieve that. Now, having said that, now let us analyze a few scenarios for this course. Yeah, so somebody said, can you repeat the optimization? So what I'm saying is, if I resolve, if let's say optimization problem is, let's say P equal to 10 bits. I want to design a 10-bit ADC, pipeline ADC, that is for sure. Okay, it's a pipeline ADC, 10 bits. Now, I can achieve 10 bits by choosing N1 equal to 1, P minus N1 as 9. Or N1 equal to 2 and this as backend ADC is 8. Any possible combination is valid. Okay. Now, the question is, what should be N1 such that our overall power consumption of this overall ADC is as small as possible? That is the optimization problem. Now, this is a very simplistic assumption. That means we have 2 stages. But a pipeline ADC will have 8 stages or 10 stages. Or this number 10, so let me say, suppose P equal to 10, right? And this can be achieved by 1 plus 9 if it is 2 stage, or 2 plus 8, and so on. Now, if it is realized using 3 stages, first stage can be 1, second stage can be 1, third stage can be 8, or 2, 1 plus 7, or 3 plus 1 plus 6, or 2 plus 2 plus 6, where that means this is a 3-stage realization. Similarly, I can have n-stage realization. So now this total resolution can be realized in different ways. Now, there are various permutations and combinations. You have to write this. That means you have to say that P equal to various number of stages. So number of stages you decide on, and then each stage resolving so many bits, the summation of those many individual bits is equal to P. That is one constraint. And the other constraint is you have to write down the power consumption of each of the stages, okay, as a function of number of bits you're resolving, and that you have to minimize, you have to find the minima of that. So it is a constraint optimization, okay. So P bits, so P bits can be achieved by let's say Q stages. Q stages, each stage resolving N1, N2, ... NQ bits, such that N1 plus N2 plus ... plus NQ equal to P, because that is the overall resolution, and the power consumption P total is minimum. Sorry for this poor way of writing, because I don't know how else I can, let me see if, yeah, there is a problem. Yeah. Anyway, so this is the constraint optimization. I hope that is clear to everyone. Okay. So now, for this talk, I am saying that let it be a 2-stage thing. Means the first case. So I will consider 1 plus 9, 2 plus 8, 3 plus 7, like that. Okay. Because manually we are analyzing. We are not writing a code or something to manually analyze. So let's say first stage is 1, next stage is 9 bits. Now the 1 bit means we need 1 bit of redundancy. We need 1 bit of redundancy here. So now 1 bit of redundancy is achieved by using a 1.5 bit stage. Now this 1.5 bit stage, as I said, this thing is realized using an op-amp along with some capacitor. So this is the overall circuit that realizes the DAC operation and the summing node and the amplification operation. Now, if you consider this, the power consumption of this circuit is a function of few things. One is, what is the feedback factor of this circuit? Okay, the feedback factor decides how much power you. Now, feedback factor, usually CS equal to CF in this, and the feedback factor is ideally half. It will be slightly less than half. Okay. Now, if I resolve one bit here, then what should be the accuracy of the residue? Because overall bits is 10 bits. So you know that if this residue should settle to the LSB over 2 of the remainder ADC. Remainder ADC is 9 bits. That means the ADC should settle to n minus p minus however many bits you resolve divided by 2. So the accuracy it will settle to is settling requirement and op-amp reduced by 1 bit. Okay. Input referred noise equal to the input referred noise here is equal to the output referred noise divided by the gain of this circuit. The gain of this circuit is 2. So it will be half of the output noise, because the input referred noise decides your noise power which comes in the denominator. Keep in mind the power is signal power divided by this noise, input referred noise, integrated noise. So now the input referred noise is what defines the noise power. So similar now, so you can see that the feedback factor is half, the input referred noise is scaled by a factor of 2, and the settling requirement of the op-amp is reduced by 1 bit. Now let us take the second case where I resolve 2 bits in the first stage and 8 bits in the later stage. Okay, so then the feedback factor, this is the circuit that realizes it. Okay, and the feedback factor is 1/4. The settling requirement of the op-amp reduces by a factor of 2 by 2 bits. The input referred noise, this circuit gives a gain of 4, so the input referred noise is scaled by a factor of 4. So this gives a good scaling factor over here. Feedback factor has become worse. So what we are seeing is now higher the feedback factor, lower would be the power consumption for a given bandwidth. Okay, basic op-amp design. So now the feedback factor reduces in this, but the noise contribution also reduces. So there is a trade-off over there. Okay, so similarly, you can go for 3 bits in the first stage. This is the circuit. This circuit provides a gain of 8 from input to output, and therefore the input referred noise is scaled by a factor of 8, but the feedback factor also reduces. Okay, so now let's go back to this. So now let us see what happens. How do we analyze this? If I have summarized only 3 cases. We can take more cases, 4.5, 5.5 in the first stage. I haven't done that. So for sake of brevity, I have kept it like this. So feedback factor for 1.5 bit is half. You can see that as I resolve more and more bits in the first stage, my feedback factor reduces. If feedback factor reduces, my speed reduces. Okay. If my speed reduces, to achieve a certain speed, I have to burn more power. So therefore, the feedback factor affects 2 parameters, speed and power. This is an offset correction range. This is, I won't get into this because the goal is not to teach pipeline ADC, but to validate the reason that how we are going to improve on the power. So it affects the linearity of the ADC. Okay. A reduction in settling time affects now if the op-amp settles to less number of bits accuracy, that means it needs less number of time constants. So I'll explain that, give you an expression of that time constant required to settle to a certain accuracy. Okay, so less number of time constants. If the less number of time constants are required by a op-amp for a given clock frequency, that means I can achieve higher speed. Okay. So, this therefore affects speed and power. The noise scaling affects SNR, power, and area. Why does it affect area? Because the noise is a function of the capacitance. We have seen KT over C. So if I have to reduce noise, I have to increase the capacitance. So it affects the area, increase the capacitance. The increasing capacitance means more and more area. So the noise scaling factor impacts the SNR power. So 1.5 bit less noise scaling means poor noise performance, means lesser SNR. This 3.5 bit gives you better SNR, right? But you have to, but speed is compromised. So you can see that feedback factor is reduced, compromising speed, noise has reduced, improving SNR. Okay, so reduction in matching requirement. So let us not get into this because this is a pipeline ADC requirement. So this affects the power and area. For resolution more than 10 bits, it is better to resolve more bits in the first stage, which relaxes the op-amp settling requirement and therefore reduces power. Therefore reducing capacitance as well, because the noise can be reduced, but it does not relax the op-amp open loop DC gain requirement. Okay, so the op-amp open loop DC gain requirement does not change. So now the question that comes up is, why not resolve more bits, 5 bits or more in the first stage, because that should give us better noise scaling, okay, and lesser settling requirement. The reason is, when I try to resolve more and more bits, the offset correction range of the ADC reduces, and when I'm sampling on 2 parallel paths, okay, then there can be timing mismatch between those two, and that could compromise the overall linearity of the ADC. Because of the timing mismatch, we'll sample a certain voltage on this path and we'll sample a different voltage on this path, and if that is exceeding the correction range, redundancy range of the stage, then we will incur nonlinearity or missing ports and missing levels. If depends on what we have, which side we exceed. Okay, now as I said, DC gain requirement of op-amp in each stage. Now the op-amp settles like this, right? So there is a slewing phenomenon followed by a settling, and it never settles to the final value. It settles to within a certain error. This error is given by, is a function of the feedback factor and the DC gain of the op-amp, and this should be less than this. Why? What is this? This is, you can see that reduction in settling requirement, number of bits that you have resolved, 3-bit reduction. So it will reduce by this much. Now if I solve, beta is 1 over n1, 1 by 2 to the power of n1. Beta is, feedback factor is 1 by 2 to the power of this, 2 to the power of 3. Here it is 3 bits, so p minus n1. So you see that if I solve this, you will end up with an expression that the DC gain of the op-amp is independent of how many bits you resolve here. You can work this out and you will see the same, see that effect over there. Now let us see how we can arrive at the power numbers based on this analysis. Okay, so these are some expressions based on simple what you called op-amp, 2-stage op-amp circuit. Now let us see. The settling time for n-bit accuracy is given by this expression. So if I have to settle to 10 bits, then I need 11 times ln2 time constants. Okay, and keep in mind a time constant defines the 3 dB bandwidth of the op-amp. Okay, so a 2-stage op-amp poles and unity gain bandwidths are given by this expression. GM1 is the gain of the first stage, transconductance of the first stage. GM2 is the transconductance of the second stage. R1 is the output impedance of the first stage. R2 is the output impedance of the second stage. So the omega P1 is nothing but this, right? CC is the compensation cap because it is a 2-stage op-amp. So GM2 R2 CC is the Miller cap times R1 is the first pole. Omega P2 equal to GM2 by CL. The second pole is GM2 by CL is the load capacitance. Omega U is GM1 by CC because we have made sure that we have compensated properly. And omega P2 is omega U. These are certain things we have taken so that we get a decent phase margin greater than 50 degrees. Okay, when you have these constraints, you get a phase margin greater than 50 degrees. Now, variance of the input referred noise is given by this expression. Now, here there are a few terms here. One is the sampled noise, one is each stage noise, then the op-amp noise comes in. Now, any reference voltage noise, that is reference voltages that are used in the circuit, those noise come in, and there is something called, because it is a sampled system, there is a clock in there, and the clock has a certain amount of jitter. It gives you jitter noise, and these will all add up in RMS sense. Okay. Now, typically we go for a second stage op amp, which is a common source stage, and we have seen in 65 nanometer and below, the GDS intrinsic gain is roughly equal to 10. So we can, for maximum output swing at the highest speed, typical gain in the second stage is 10. We can just do it with a common source stage with an intrinsic gain of 10. Okay. Overdrive voltage to maximize swing is chosen to be around 150 millivolts. Okay, we have chosen the overdrive voltage. Overdrive voltage is the VGS minus V threshold in long channel devices. It will be slightly different in case of short channel devices. And in current in each branch in a 2 stages, our ID1 is given by GM1 times the overdrive voltage. Let me just correct this. Sorry. Let me correct this thing because there is a type, I don't know, it didn't come in subscript. Oh, it is not doing it. Okay. And ID2 is GM2 times the V overdrive voltage by 2. This is the basic expression of a long channel device, square law device. Okay. Now, let us try to design something in which the signal swing is plus minus 70 millivolts, 750 millivolts. That means my V peak to peak is approaching the supply voltage. We can always do that because it is a differential circuit. Okay, so that we have purposely chosen it this way. 1.5 volt is the supply voltage. 750 millivolts plus minus 750 means we know that we can achieve the minimum power, the lowest figure of merit. Okay, resolution is 12 bits. Our maximum input signal is 100 megahertz and the sample rate is 200 megahertz. We are giving a slewing time of 0.5 nanoseconds, non-overlap because we need non-overlapping clocks, and the settling time of 1.8 nanoseconds. So these are certain numbers because these numbers will be useful to come up with the pole locations and all. Now, noise budget includes the quantization noise, sample thermal noise, op-amp noise, reference noise, jitter noise, and input signal buffer noise. All these noises are there. When you consider all of them, and the jitter variance is given by this. Okay. So 2 pi Tj, and usually Tj is given by the manufacturer of the PLL. Fin is the maximum input frequency, which is 100 megahertz in this scenario, and A is the amplitude, which is plus minus 750. And if you plug in these values for a maximum input, the jitter limited SNR of 80 dB requires an RMS jitter of 700 femtosecond. Okay. Now, what is this jitter limited SNR of 80 dB, which I have not mentioned, but I usually teach this in an ADC course. So, but let us say that we are targeting a 12-bit system, which is 74 dB. So we want the jitter limited SNR to be 6 dB lower than the overall performance of the overall SNR of the ADC, so that the jitter does not degrade the SNR of the ADC. Okay, so that's why this 80 dB has been chosen. So 80 dB is what? 80 dB is 12 bits is 74 dB. 12 bits plus 6 dB. 74 plus 6 is 80 dB. That's what we came up with. Now, if we find out, therefore, the quantization noise power is 366 microvolts. Okay. Reference noise is 90 microvolts. Op-amp noise, this is some design I had done. Sample noise for a 2 picofarad sampling capacitance, differential, keep in mind, KT over C, it will become twice KT over C, it is 64 microvolts. Jitter noise is going to be 66 microvolts for 200 femtosecond of RMS jitter. And overall SNR that we achieve is 67.8 dB. Now, although we are designing a 12-bit system, now you can clearly see that we are never achieving the SNR of a 12-bit, which is 74 dB. The reason is our denominator has lot of other noise components. So therefore, lot of the designs that we design have, lot of the design circuits that we build, a lot of them are thermal noise limited. Okay. And in order to overcome the thermal noise, we go for averaging to remove the thermal noise and achieve more and more SNR. That means we achieve more and more SNR at the expense of averaging, resulting in the reduction of the bandwidth. Okay, so I did some analysis based on that, and as I have said, 9 architecture has 1.5 bit stages, different combinations of them, and finally the power that we achieve is 50 milliwatts. Okay, so those of you who want to learn how I came up with these numbers, I can share an Excel sheet which actually summarizes all of them. Okay, so we can which actually summarizes how we come up with this. Okay, so basically this architecture is the optimal architecture. Okay, so but we are not achieving the SNR of a 12-bit. We are thermal noise limited SNR of 66 dB is what we achieve. But this architecture, all of them achieve almost a similar amount of SNR, but this achieves the same SNR with lowest power. Okay, so that is what with that I would conclude the section on the power optimization. Of course, I did not get into how I arrived at these numbers, arrived at this calculation. There is an Excel sheet. If in tomorrow's class where I'm talking about noise analysis, that's where I'll go through this Excel sheet in more detail. But here I wanted to bring to the note that we do all these things for really low power optimization, but this is done manually by hand. This can always be coded, and you can do geometric programming or machine learning to do this optimization and come up. If you can write a cost function and arrive at the right result, that will be that can be a very nice research publication as well. Okay, any questions on this so far? We'll discuss more about this in tomorrow's lecture in the noise analysis. How we arrived at these numbers. Any questions on this? Okay, so now digital circuits for analog processing. So I want to delve into this circuit because this circuit has a lot of relevance in the modern day context where everybody wants to do some kind of machine learning and all. Okay, so what I'm proposing is a ring oscillator based sub 1 volt DC integrated fire neuron. So we'll show how people have implemented in olden days neurons using op amps and other analog circuits. What are the drawbacks of those, and then how can I use a ring oscillator, which is a purely digital circuit, to build a neuron circuit and therefore do some machine learning, character recognition or something else. So silicon neurons are the heart of neuromorphic circuits. Okay, various implementation styles listed below have been used in the past. Voltage mode or current mode have been used. Weak inversion and strong inversion circuits have been used. Non-clocked and switched capacitor neurons have been built. There are also real time and accelerated time. So what is real time? The way we work is real time. The neurons will be operating at our speed of the human in milliseconds and all. The accelerated time means they'll be operating at the very highest frequency. Nanosecond electronic circuits operate at very high speed. So accelerated time, that's the difference between real time and accelerated time neuron. Now, ring oscillator based silicon neuron lends itself to low voltage implementation alongside complex digital circuits to implement brain inspired computing. So this was one of the oldest neuron proposed by Carver Mead called the axon hillock, okay, in 1974 or 75. I don't remember exactly, from Caltech. So what happens is that you realize an integration operation, okay, and then what you do is when the output toggles goes high, okay, then you discharge this so basically there is an inverter, there are two inverters. When the voltage goes high or voltage goes low, then this output voltage is going to, when this voltage goes high, then this output voltage is going to go high. As soon as this goes high, then what happens is that this membrane potential of a neuron is going to get discharged. So discharged, and again then it will come back to 0, because this will go to 0 and therefore this will come back to 0. So what is so therefore you are integrating onto this membrane capacitor, integrate. Then once you have integrated, reach a certain voltage, you fire the neuron, you get a spike. That spike turns on this feedback circuit and then discharges this thing, and so therefore it is called an integrate and fire neuron. Okay. Following drawbacks, the inverter, now what happens is that this inverter, this first stage inverter, is driven by this potential here, membrane potential. Now when this is rising, it will draw a lot of short circuit current. Now if I want to implement this in real time, means in milliseconds, I need a huge capacitor. Okay, this will be very area hungry. So that means in a single chip, I cannot implement a lot of neurons. Hundreds of neurons cannot be implemented. But accelerated time scale could be efficiently implemented, accelerated, but there will be power consumption here. Lack of explicit, so refractory period and spike frequency adaptation are two important parameters of a neuron, which are needed because of the way we function is, if we know that we are recognizing a pattern, our neurons start firing more and more frequently. So that is called spike frequency adaptation. And then the refractory period is how long it takes to give you another spike. Okay. So these are two controls that are difficult to control in this circuit. So this was the very preliminary neuron model that was built. Okay. So now people said that, okay, why go for that? Why not use an op-amp? So they go in for a voltage mode implementation. So what they did is there is a membrane potential and there is a resistance which leaks the charge across this. So this is acting more like a low pass filter. Okay. So integrate and fire, and there is a spike generator so that the output voltage, when the output of the op-amp exceeds the threshold voltage here, then the comparator becomes 1, it generates a spike, then resets this thing, discharges this membrane capacitance. Same like this, but uses an op-amp. Again, real-time silicon implementation would require large CMM, which would require large area. And also op-amp requires large supply voltage to realize moderate gain op-amps. If the gain of the op-amp is not good, then it is not going to work like a good integrator. Okay. So area efficient biological time scale neurons are difficult to implement using op-amp based circuits. Okay. Now let us see what we can we do something better. Now, if I have an integrator, okay, with a unity gain bandwidth of alpha, this integrator has a unity gain bandwidth of alpha, and I put unity gain feedback around it, then the 3 dB bandwidth of this circuit is equal to alpha radians per second. So I could take an integrator, put unity gain feedback around it, and achieve a low pass filter, which is exactly what this circuit is doing. This is exactly a low pass filter. Okay. Now, this can be a voltage control oscillator, behaves like a perfect voltage to phase integrator, can be used to realize a low pass filter. Now, keep in mind here the dimensions are changing, voltage to phase. A VCO acts like a VCO. If I have a V in and I take the phase out and I take phi out divided by V in, then this is a perfect integrator. But K VCO is the voltage gain. Now, but I have to generate voltage. So what can I do? So I can use, how do we generate voltage in case of, if I have the phase, I can use a phase detector, XOR phase detector with a reference phase. And therefore I can generate, this waveform will be a pulse width modulated signal, PWM signal. So the input voltage is coming of a certain frequency, and then this V out will be a PWM signal, which will be, if the amplitude increases, pulses will be more. If amplitude reduces, pulses, low pulses will be longer. Otherwise, high pulses will be longer. So this is high voltage, this is low. So it is exactly giving you this. But the drawback is that this is square wave, so it will have tones. If Fin is there, it will have tones at FREF, 2FREF, and the side bands are this FREF minus Fin, FREF plus Fin. So you will have these side bands which are sync attenuated. So now that means the output of this is a faithful representation of this, an integral of this, right? But it is an integral of this, but in order to get a perfect integration, I have to have a sharp low pass filter, which is difficult, means I need a large capacitor. So what can we do? Can we move this far apart? Can we move this away from this input as much as possible? The answer is yes. If I take multiple phases and then use XOR gates and use a resistor to sum them up, then the phases, these voltages are operated. If there are M phases, then the reference frequency, it switches to MFRF. This FRF sideband will move to MFRF. Then I can filter this out using a very crappy low pass filter. So if I use, let's say 16 or 32 phases, this is 32 times FRF apart. So I can easily use a single pole, very small R and small C to filter out these sidebands, these notches that are coming. And therefore, I get from voltage to phase, now I'm getting voltage out to V out to V in. So here it is phase out. I use a pulse width modulator and a filtering operation. This R does the filtering operation as well, and the summing node, and gives me V out, and we get a transfer function which is a perfect integral. Okay, so now can I use this to realize a structure which is all digital? The answer is I have to now realize the circuit. Now, if I have to realize the circuit, the transfer function is given by this. How can I realize this circuit using this? I know that from here to here, this is behaving like an integrator. I put feedback RF and RS around it, and therefore I get a VCO based low pass filter given by this expression. You can all simulate this. Okay, and you can see that the bandwidth 1 over RFCF is the 3 dB bandwidth. The bandwidth is given by this expression here, these things. It's a function of KVCO. KPD is equal to pi, because it's a X of phase detector gain. KPD is the phase detector gain. RF and RS are the resistors. Okay. This is published in the ISCAS 2017, and we are building a character recognition circuit using this circuit now in 180 nanometer. So this is the basic low pass filter. This is called a analog. This is realizing a low pass filter exactly like this, but does not use op amps, and therefore it can operate at very low supply voltage. Okay. Now, and then we have realized this. So we have mixed and matched two different devices, 2.5 volt and 0.9 volt supply. 2.5 volt thick oxide devices are used, and 0.9 volt supplies, so that we can use real-time silicon implementation, real-time silicon neuron, which are operating in milliseconds. Now, in order to implement, so now low pass filter, if I give a step response over here, then the output should reduce. If I give a step response, the output, so, and we get this output depending on if I can vary the KVCO. Okay. If I want various time constants, I have to vary the KVCO. Because why do we vary the KVCO? Because we don't want to vary this RF and RS, because these are fixed and it is very difficult to vary them. But I can vary the KVCO of the circuit in a digital manner. And this can be varied by using a current starved inverter with different amount of programmable transistors. And we can use this to vary the KVCO and achieve whatever amount of time constant that I want. But if I want a real-time silicon neuron, I go for this time constant. If I want an accelerated neuron, I can go for this time constants. Very sharp, smaller time constant. So the larger the number of transistors connected to Vin, the larger the KVCO. Now, a neuron has multiple inputs, okay, and one output it gives you, and those outputs again feed into the different, so there are synapses. So now we can consider this as a synapse. So n inputs are coming in. Now this is like a summing amplifier, right? In an op amp, I can, in this op amp circuit, if I have V in 1, V in 2, I can put multiple RS and like this, and it becomes a summing, integrating leaky low pass filter. So exact same thing is done here. We can do this, and then we are adding some refractory period control over here, and we can adjust the spike frequencies as well to mimic as the way the neurons in our brain behave. Okay, so this one does the programmable refractory period, adapt the spike frequency, all those things can be incorporated. Now, if I write down the transfer function V out over V in over here, we get the V out over V in is given by this expression. So it is just a simple op-amp with various summing node amplifiers. So you are summing up V in 1, V in 2 based on different gains, RF divided by this. Okay. Spike is driven by a clocked comparator. Now you might say that if this is a clocked comparator, how is it going to know when this comparator should be asynchronous, right? Because this spike. Now the thing is that these oscillators are operating at a much higher frequency than the neuron is supposed to operate, because as I have said, this we have to push these frequencies high out. Okay, so therefore the reference frequencies will be decently high enough so that this can do a filtering operation. So therefore we can use this reference frequency. We'll have a M phase VCO and we'll have a reference VCO as well. Yes, please go ahead.
This V reference is equal to V bias in the neuron, is it?
V reference will be the V bias in the neuron, yes.
Okay, sir. In that case, these neurons will give the output directly from the inputs. That means these neurons will not require any coding actually.
I'll get into that. It requires training also. So I'll tell you how do you train them. Okay. So you will be training them, and those training values will come from a simple resistor ladder resistive DAC, because we are not operating at very high frequency.
Okay.
Right. So there are some training things. We'll show how the training coefficients will be programmed onto a digital D flip-flop and control the DACs and adjust the training, adjusts this spike frequency and the refractory period. Because if I see a cat or see a letter, let's go for character recognition. If A comes in, then one neuron should fire more frequently. Or A has come in. If B comes in, another should fire more frequently, and that is where the training comes in. So that's where the programmable refractory and the spike frequency comes in. Yes, there is somebody, Mr. Venu E, has put a chat. Hi. Okay. So now this is the overall transfer function. So you need this reference frequency. There are a lot more details here which I cannot go over because there is not much time. So why we need these multiplexers and all, so that we can reset the phase, because this thing has to be reset in a manner that when the next spike has coming, it should be able to respond quickly. So all those things are there. So so let me go into yes. Now how do you control the refractory period? So now the spike that comes in, okay, so the refractory period control here, the spike that comes in has to be appropriately delayed. If I want that, okay, when B comes in, the A neuron should not fire. It should fire less frequently compared to the B1, let us say. So that means, how do I make sure that the A neuron doesn't fire? So what we'll do is we'll have the spike coming in, going to a current starved inverter followed by a comparator. Now, if I adjust this bias voltage, that means this node is going to discharge based on this current. And if it is discharging slowly, I get more and more discharge slowly. I'll have spike frequency will be smaller. If I increase this voltage higher and higher, my spike frequency is going to go higher and higher. Okay, so this is how we adjust the spike frequency, and then adjust the refractory period. Refractory period, how far off, and how do we adjust the spike frequency? We can adjust the spike frequency by changing the 3 dB bandwidth of the low pass filter. Now, how do we change the 3 dB bandwidth of the low pass filter in a digital manner? You can see that the 3 dB bandwidth, we don't want to change the resistors because these are fixed. We don't want to put programmable resistors because that will add area. So what do we do? KPD is fixed. It is pi. It is the phase detector gain. We can adjust the KVCO. So we adjust the KVCO by using this programming technique, digital programming. So by adjusting the KVCO, we can adjust the 3 dB bandwidth. Also, we can change the threshold voltage of the comparator. So now the spike rate, the spike here will be, if I increase the threshold voltage, this will take longer time to charge and discharge. So therefore, the spike rate will also go. So we have two controls. One is the KVCO as well as the threshold voltage to adjust the spike frequency. So here I am showing that the spikes are coming like this and less spikes are coming as I keep on increasing the discharge time, the V out, as I keep on increasing more and more. So this is by adaptation by changing KVCO. So with this, I think I'll stop the lecture. I'll entertain some questions. So we have discussed two, and tomorrow we'll go into the details of how the noise analysis and how did we use those equations to arrive at those power numbers. We'll go into details of those. This kind of neuron can be implemented. This is all digital. It can also work at 0.5 volts. It can go down all the way. In 180 nanometer, we are trying to make this work at 0.5 volts. Okay. And we are trying to build character recognition algorithms. So when you operate at 0.5 volts, your power will be very, very less. So this is all that I have for the low power analog design aspect of it. Thank you all. Any questions?
Sir, regarding deep neural networks, can
Yes.
we just implement those deep neural networks directly through neuromorphic computation?
We are implementing CNNs. You're not using this one, using capacitors. We are doing it.
Yes.
Right now, we are building a chip which can do capacitor-based addition dot product computation, and we are using a bunch of ADCs and DACs.
There is a question in the chat box, sir.
Yeah. Yeah, there are opportunities. They can come for summer or something, and we can they can stay here and work. There is no problem. There are some ways that you have to apply through ERP and all in our system, and then somebody can come over and work here. There is no problem at all.
Sir, regarding artificial neural networks, is it advantageous to have compute these things in neuromorphic computation than digitally through programming?
I mean, now it depends. For example, when we try to build, let's say, CFAR10 image classification algorithm on an FPGA, which is purely digital, right?
Yes.
The power consumption is pretty high, and if we go for LXNet and VGGNet and Tiny Darknet and all, we are getting power numbers close to 2-3 watts. Sometimes it goes all the way up to 5 watts in digital. But if we do, and most of the power consumption is in the memory access. Okay,
Yes.
because there are so many filter coefficients and all. Now, if we can program them, if we can do some, instead of accessing the memory, we can do some computation inside the memory itself. Right, or we can do some operations inside the image sensor itself. Right, some dot products can be done inside the image sensor. Then we get a huge advantage.
Yes, sir.
Okay, so those are some things we are exploring. We don't have a chip yet. We are trying to, because I don't have access to image sensor PDK. So we have some circuits that can do that. We are working on those, but no, nothing concrete as of now. Another year or year and a half we'll have that.
Yes, sir.
Any other questions? If none, then probably we can stop the lecture at this point. Talk. Yeah, about delta sigma, tomorrow there is noise thing, so I will get into the noise aspect and discuss a little bit about delta sigma. But the ADC to cover in 2 hours is very difficult. I mean, to have an ADC thing, you need at least 1 week of at least 10 to 12 hours of talk time to cover at least some aspect of ADCs.
Okay, I thank Bibhu Dutta Sahoo sir for his informative talk, and we hope to meet him again tomorrow in the second session. So thank you all of you for your
Thank you.
kind hearing.
I'll email the slides to you so that you can share it with all the participants.
Okay, sir. Okay.
Okay. Okay then. Thank you.